Imagine for a moment the silence of space, a vast, dark canvas stretching beyond comprehension. And then, without warning, a fleeting crackle of cosmic energy surges through the emptiness, a burst of radio waves so intense it outshines entire galaxies, yet lasting only a few thousandths of a second before vanishing back into the void as if it were never there at all. This phenomenon, known as a fast radio burst or FRB, is one of the universe's most baffling and electrifying mysteries. It's a ghost signal, a cosmic whisper that defies explanation, challenging everything we think we know about the nature of reality itself. What could possibly generate such staggering amounts of energy in such an impossibly short span of time? Are these bursts evidence of colossal stellar explosions, messages from advanced civilizations, or perhaps something stranger, something we haven't even dreamed of yet? Each new detection deepens the intrigue, pulling us further into a puzzle that spans the cosmos. For decades, astronomers have trained their most powerful instruments toward the skies, hoping to catch these elusive signals and decode their origins. Yet with every answer, new questions emerge, pulling back the curtain on a universe far more mysterious and dynamic than we ever imagined. In this video, we're embarking on a journey to explore 30 of the greatest enigmas surrounding fast radio bursts, each one a story written in radio waves, echoing across billions of light years. Together, we'll venture into the heart of deep space anomalies, untangle the threads of scientific speculation, and stand at the frontier of human curiosity. This isn't just about distant cosmic events. It's about what it means to reach into the unknown and seek understanding in the face of the sublime. So settle in, open your mind, and prepare to explore the uncharted territories of the universe, where every burst holds a secret and every mystery beckons us further into the wonder of it all. At the very heart of the fast radio burst enigma lies the origin problem, the first and most fundamental mystery that astronomers faced. Picture this: you're sitting in a pitch-black theater, and for just a single, fleeting moment, a fraction of the time it takes to blink, a colossal flashbulb goes off on the other side of the universe. It's overwhelmingly bright, and then, just as suddenly, it's gone, leaving you with nothing but the afterimage and a cascade of questions. That is the essence of an FRB. These events pack a staggering amount of energy. We're not talking about a simple spark. A single fast radio burst can release more energy in a few milliseconds than our sun puts out over several decades. To generate that kind of power so instantaneously requires a cataclysmic engine, something far beyond the scope of ordinary stellar phenomena. The sheer violence of it is what first captured scientists' attention and continues to baffle them today. The challenge of figuring out where they come from is magnified by the incredible distances involved. These aren't local events happening in our galactic backyard. The signals we detect have traveled across billions of light years, their waves stretched and weakened by the expansion of the universe itself. Pinpointing the source of such a brief, faraway signal is like trying to identify a specific firefly flashing once in a dense forest from an airplane flying miles overhead. You have only that one blink of data to work with. For years after the first FRB was discovered in 2007, astronomers didn't even know if they were originating from within our own galaxy or from the deepest reaches of the cosmos. This ambiguity meant that for a long time, every proposed explanation, from evaporating black holes to clashing neutron stars, was purely theoretical. The real breakthrough came when we started to detect repeating bursts, signals that would flash from the same patch of sky multiple times. This repetition ruled out one-time catastrophic events, like a star exploding, and pointed toward a source that could survive these immense outbursts, something that could fire again and again. This was the first major clue in a long investigation, a hint that the universe was hiding a new class of object capable of such ferocious and repeated power. The origin problem is the doorway to all the other mysteries. the primary question that every new telescope and observation campaign is desperately trying to answer. Just when astronomers thought they had a handle on the sheer strangeness of these signals, the universe presented an even deeper layer to the mystery. We moved from asking what could possibly create such a brief, immense flash of energy to confronting an even more baffling question. What could possibly create such a flash, survive it, and then do it again? And again and again. This is the core of our second great mystery, the stark and puzzling division between one-off, non-repeating bursts and those that repeat from the same point in the sky. This dichotomy didn't just add a new question, it fundamentally reshaped the entire field of FRB research, forcing scientists to reconsider every theory they had. For the first few years after their discovery, every detected fast radio burst was a solitary event. It would flash into existence with unimaginable power and then vanish forever, never to be heard from again. This behavior pointed strongly toward a catastrophic, one-time source. The leading ideas were things like the final death cry of a supernova, the cataclysmic merger of two incredibly dense neutron stars, or a black hole suddenly evaporating in a burst of Hawking radiation. These are events of cosmic finality. They happen once, they are unbelievably violent, and then there's nothing left to cause another burst. This explanation was clean, elegant, and fit the data we had. But the universe rarely favors simple answers. Then, in 2015, everything changed. Astronomers using the Arecibo Observatory in Puerto Rico made a stunning announcement. They had found a fast radio burst, designated FRB 121102, that was repeating. This wasn't a one-off cataclysm. It was a source that was actively and seemingly randomly firing off multiple bursts. Some were strong, some were weak, with no discernible pattern to their timing. This single discovery blew the door wide open. It meant that whatever engine was powering these events had to be something that could not only survive its own outburst but also recharge and fire again. You can't have a star explode twice. You can't have two neutron stars merge a second time. The repeating burst immediately ruled out an entire class of theories based on single, self-destructing events. This revelation suggested that there might not be one single answer to the FRB enigma, but perhaps two or even more. We now had to consider that the population of fast radio bursts could be coming from at least two distinct types of cosmic phenomena, one that destroys itself in a final, glorious flash, and another that is a persistent, repeating engine of incredible power. The repeater, FRB 121102, quickly became the most studied object in the FRB catalog. By having a source that kept transmitting, astronomers could point the world's most powerful telescopes at its coordinates and wait, finally gathering enough data to pinpoint its home galaxy, a dwarf galaxy over 3 billion light-years away. This confirmed their extragalactic origins and provided a crucial environmental clue. The existence of both repeaters and one-off bursts suggests we might be looking at different stages in the life of a cosmic object, or entirely different mechanisms altogether. Perhaps the non-repeaters are indeed the final, fatal collisions of exotic stars, while the repeaters are caused by a young, highly energetic type of neutron star called a magnetar, whose intense magnetic fields can crack its crust and unleash torrents of energy without destroying itself. Or maybe the repeaters are something even more exotic, like a pulsar orbiting a black hole, being periodically triggered. The divide between these two types is one of the most active areas of research today, a fundamental split that tells us the universe has more than one way to write its most powerful, fleeting messages. But the sheer scale of these bursts pushes even our most extreme astrophysical engines to their absolute limits. To truly grasp the third great mystery, we must grapple with the almost incomprehensible energy output of these events. Think of the Sun, that colossal sphere of fusing plasma that has sustained life on Earth for billions of years. It is a constant, reliable torrent of energy. Now, imagine compressing all the light and heat our sun radiates over an entire month, or even several decades, and then releasing it all in a single, blinding flash that lasts less time than it takes for a hummingbird to flap its wings. That is the prodigious, almost violent energy density of a typical fast radio burst. The numbers are staggering. A single millisecond burst can release upwards of 10 to the 38 ergs of energy. To put that in human terms, that's equivalent to the total energy output of 500 million suns, all focused into a blink of an eye event. This isn't just a bright flash, it is one of the most energetically efficient processes we have ever witnessed in the entire universe. The physics behind generating such extreme energy densities in such a short time frame is the central puzzle. Energy requires a source, and to release it so quickly requires an engine of unimaginable power and precision. The leading theoretical model points to a specific type of neutron star known as a magnetar. Neutron stars themselves are already the remnants of stellar cataclysms, the ultra-dense cores left behind after a massive star goes supernova. A magnetar is a neutron star on steroids, possessing a magnetic field so intense it defies belief, 1,000 trillion times stronger than Earth's magnetic field. If a magnetar were located halfway between Earth and the Moon, its magnetic field would effortlessly strip the information from every credit card on the planet. In such an environment, the star's crust is under immense strain. Theorists propose that these magnetic fields can become twisted and stressed over time, eventually causing a starquake, a sudden fracturing of the neutron star's rigid crust. This seismic event would release a titanic amount of pent-up magnetic energy, accelerating particles to near light speed and creating a fireball of radiation that we would detect as a fast radio burst. This model elegantly explains the incredible energy output and, crucially, the repeating nature of some FRBs. The crust can fracture multiple times, creating multiple bursts from the same object. Other models venture into even more exotic territory. One compelling idea involves the cataclysmic collision of two incredibly dense objects, like neutron stars merging or a neutron star being consumed by a black hole. The final moments of such a merger would be a frenzy of unbelievable violence, rippling space-time with gravitational waves and potentially powering a short, incredibly bright burst of radio emission as the final fragments of matter are shredded and accelerated. This scenario is a strong candidate for the one-off, non-repeating FRBs, as the event is, by its very nature, final and destructive. Another, far more speculative theory suggests phenomena involving cosmic strings or the evaporation of primordial black holes left over from the Big Bang. These ideas push the boundaries of known physics, suggesting that FRBs might be our first experimental window into realms of theoretical physics we have only ever described with equations on a chalkboard. Each model is a testament to human ingenuity, an attempt to explain the seemingly impossible by stretching our understanding of the cosmos to its breaking point. The energy output of an FRB is not just a number, it is a direct challenge, a cosmic dare that compels us to imagine what kind of universe could possibly forge such a momentary and magnificent inferno. Early on, the most basic question about these mysterious signals was also the most divisive. Just how far away were they? The debate over whether fast radio bursts were local events within our own Milky Way galaxy or messengers from vastly more distant galaxies wasn't just academic. It fundamentally shaped every single theory about what they could be. This was a classic scientific detective story, a puzzle where the first clue, distance, would either narrow down the list of suspects to a handful or blow the case wide open into the unimaginable vastness of the entire cosmos. The initial evidence was frustratingly ambiguous. When a signal travels through space, it doesn't just get weaker, it interacts with the sparse sea of electrons that fills the space between galaxies. This interaction leaves a specific fingerprint on the radio waves called dispersion. a delay where higher frequency waves arrive at our telescopes just a tiny fraction of a second before the lower frequency waves. The greater the amount of this dispersion, the more material the signal has traveled through, suggesting a longer journey from its source. The very first FRB detected, the Lorimer burst, had a huge dispersion measure. It was so large, in fact, that if the burst had originated within our galaxy, the density of electrons needed to cause that much delay would have been implausibly high. The math strongly suggested an extragalactic origin, a journey of billions of light years. But for many scientists, that conclusion was almost too extraordinary to accept without more direct proof. Could our instruments be miscalibrated? Could there be some unknown, extremely dense patch of plasma within our own galaxy that was mimicking the signature of an immense distance? The possibility remained that these were relatively nearby, albeit still powerful, events from within the Milky Way, perhaps from exotic objects like flaring magnetars or peculiar pulsars we simply hadn't categorized yet. The turning point in this great debate came with the painstaking work of localization. To truly settle the argument, astronomers needed to do more than just measure a signal's dispersion. They needed to pinpoint its exact cosmic address. This required a new generation of radio telescopes with incredibly high resolution, capable of narrowing down a burst's location to a specific patch of sky small enough to then point optical telescopes at it and see what was there. The breakthrough arrived with the repeating source FRB 121102. Because it kept flashing, astronomers had multiple chances to train networks of telescopes on its position. They eventually succeeded in triangulating its location with astonishing precision, tracing it not just to a specific galaxy, but to a specific region within a tiny, faint dwarf galaxy over 3 billion light-years away. This was the definitive proof. The burst wasn't just coming from outside our galaxy. It was coming from a galaxy so distant its light had been traveling for nearly a quarter of the current age of the universe. This single confirmation transformed the field. It meant the energy requirements for FRBs were even more staggering than previously thought, as the signals had to be bright enough to be detectable across such a mind-boggling gulf of space. From that moment, the extragalactic nature of most fast radio bursts was firmly established. Yet, in a wonderful twist that science often provides, just as the debate seemed settled, the universe offered a fascinating exception. In April 2020, an immensely powerful millisecond radio burst was detected from a known magnetar within our own Milky Way galaxy, just 30,000 light-years away. This event, named FRB 2428, was a game-changer. For the first time, we had a front-row seat to a phenomenon that had previously been a distant mystery. We observed a simultaneous flash of X-rays from the same object, directly linking at least one type of FRB to the hypermagnetic outburst of a magnetar. This nearby event didn't invalidate the extragalactic discoveries. Instead, it complicated the story beautifully. It proved that the engine for these bursts could indeed exist close to home, suggesting that the population of FRBs we detect might be a mixed bag, a chorus of signals from both incredibly distant galaxies and very rarely from within our own. This keeps the debate alive in the most thrilling way, reminding us that while we have found answers, the cosmos always retains a few surprises. This journey of a fast radio burst from its mysterious source to our telescopes is far from a simple trip through empty space. Every single wave carries a hidden story, a cosmic diary entry of everything it has passed through on its billion light-year voyage. The key to reading that diary lies in a subtle but telling characteristic called the dispersion measure. When an FRB signal finally reaches us, its higher frequency radio waves arrive at our detectors a fraction of a second before the lower frequencies. This delay isn't a flaw in the signal, it's a precious clue. It's caused by the radio waves interacting with free electrons, the fundamental particles that are scattered almost everywhere in the universe. Each electron these waves pass slightly slows them down, and this effect is just a tiny bit stronger for lower frequencies than for higher ones. The greater the delay between the highest and lowest notes of the burst, the more electrons the signal has had to travel through, which generally points to a longer journey from its source. It acts as a cosmic odometer, giving us a rough estimate of the distance the burst has traveled. But this is where the mystery deepens from a simple measurement into a genuine enigma. Once astronomers began to pinpoint the home galaxies of various FRBs using other methods, they could calculate the expected dispersion measure for that specific distance. The math is based on our best models of the universe's large-scale structure and the average sparse density of electrons that fills the vast voids between galaxies. Time and again, however, the actual dispersion measure observed in many FRB signals is significantly higher than this predicted value. There's an unexplained excess, a surplus of delay that shouldn't be there if the signal only traveled through the known intergalactic medium. This discrepancy is the dispersion measure enigma, and it whispers a tantalizing possibility that these signals are picking up extra baggage on their journey from an unknown source of electrons that our current maps of the cosmos are missing entirely. So where is this extra material? Scientists are investigating two compelling and equally fascinating possibilities. The first is that the excess electrons are part of the FRB's local environment, a dense, murky halo of plasma that surrounds the source itself. Imagine a lighthouse beacon trying to shine through a thick, persistent fog on the coast. The light is blurred and delayed before it even enters the clear, open ocean. If an FRB originates from within a supernova remnant, a nebula of hot gas, or the intense magnetosphere of a young magnetar, its signal would have to fight through this dense cocoon of particles first, acquiring a large dispersion measure right at the start of its journey. This would mean the extreme environment of these cosmic engines is even more complex and energetic than we thought. The second possibility ventures into the truly unknown realms of intergalactic space. Our maps of the universe between galaxies are still rudimentary. We know it's not completely empty, but it's often described as a near-perfect vacuum. The dispersion measure excess challenges that simplicity. It suggests the existence of previously undetected structures, invisible filaments of warm gas, faint halos around galaxies, or even entire missing reservoirs of what astronomers call the missing baryonic matter. For decades, cosmologists have faced a puzzle. A portion of the universe's normal matter, the kind that makes up stars, planets, and us, seems to be unaccounted for. It hasn't been detected in stars or neat clouds of gas. This enigmatic excess dispersion in FRB signals might be the first direct evidence of where that missing matter has been hiding, tied up in diffuse, hard-to-see webs of hot gas stretching between galaxies. Each new FRB we detect with a precise location acts like a single probe sent into the cosmic dark, and by collecting enough of them, we are essentially building a first-of-its-kind map of this invisible material. The dispersion measure, therefore, is more than just a distance gauge. It is becoming a powerful new tool for cosmic cartography, using these brilliant flashes to illuminate the shadows in our universe. Beyond the extraordinary energy and the dispersion puzzle, the radio waves of a fast radio burst can carry yet another subtle, but immensely telling, fingerprint of their journey. This is the mystery of the scattering tail, a characteristic that appears not in the timing of different frequencies, but in the very shape of the signal itself. When we look closely at the light curve of some FRBs, we see that the millisecond flash doesn't have a perfectly sharp beginning and end. Instead, the tail end of the burst can appear stretched or smeared out, like a bright star viewed through the rippling heat haze of a desert highway. This effect, known as pulse broadening or scattering, is caused by the radio waves encountering turbulent, clumpy plasma along their path. As the signal propagates through this chaotic material, different waves take slightly different paths. Some are delayed more than others as they navigate the dense pockets of electrons. This multi-path travel forces the originally crisp pulse to spread out in time, arriving at our telescopes as a faint, extended echo of itself. This scattering tail is far more than just a distortion to be corrected. It is a powerful diagnostic tool, a cosmic weather report from the most extreme environments in the universe. The degree of scattering tells astronomers about the density and turbulence of the plasma the signal has passed through. A heavily scattered signal points to a journey through a veritable fog of high-energy particles. The key question is, where is this fog located? The evidence increasingly suggests that for many FRBs, this turbulent plasma isn't spread evenly across intergalactic space, but is instead packed tightly into the immediate neighborhood of the source itself. The most strongly scattered bursts seem to originate from within incredibly dense and violent environments, like the expanding shell of a recent supernova remnant or the turbulent heart of a star-forming nebula. These are places where massive stars live fast and die young, ejecting their outer layers in colossal explosions and leaving behind chaotic clouds of hot, ionized gas. This connection provides a crucial clue about the life cycle of the objects that produce FRBs. A young, highly active magnetar, for example, is often born in the fiery aftermath of a supernova. For thousands of years after its birth, it would be nestled deep within the expanding cloud of debris from its progenitor star's explosion. Any signal it emits, including a powerful FRB, would have to first punch through this thick, chaotic shroud of plasma, acquiring a significant scattering tail in the process. As the supernova remnant expands and dissipates over hundreds of thousands of years, the environment around the magnetar would gradually clear and the scattering of its signals would lessen. Therefore, by measuring the scattering tail of an FRB, we might essentially be able to estimate the age of its source and the density of its stellar nursery. A heavily scattered burst could be the cry of a cosmic newborn, while a cleaner, unscattered signal might come from an older, more isolated object. This turns a simple anomaly in the data into a window onto the life story of these enigmatic engines, allowing us to peer not just at the burst, but into the dynamic and violent cradle from which it came. For all their staggering energy, fast radio bursts have a perplexing habit of being incredibly stingy with their light show. You might logically assume that an event capable of releasing the energy of 500 million suns in a millisecond would light up the sky across the entire electromagnetic spectrum, a brilliant, simultaneous flash of visible light, a surge of X-rays, a blast of gamma rays. Yet, time and again, when one of these radio shouts is detected, astronomers around the world scramble to swing every available telescope optical, infrared, ultraviolet, X-ray toward its coordinates, and almost always they find nothing. The radio burst is a solo performance in an otherwise dark and silent theater. This is the mystery of the missing counterparts, a frustrating cosmic game of peek-a-boo that challenges our very understanding of how these immense explosions work. This absence is deeply telling. In astrophysics, the specific blend of light an object emits, its multi-wavelength signature, acts like a fingerprint, revealing the physical processes at work. A supernova, for instance, produces a predictable cascade of light, from gamma rays created in the initial shockwave to the glowing shell of expanding debris we see in optical telescopes for months or years afterward. The fact that FRBs overwhelmingly lack these accompanying signals suggests that the engine powering them is uniquely efficient, somehow channeling nearly all of its colossal energy exclusively into radio waves. It's as if a bomb were designed to release all of its power as a single, incredibly loud sound with no flash of light, no heat, and no shrapnel. This forces theorists to consider emission mechanisms that are exceptionally clean and focused. One compelling idea is that the radio emission is highly beamed, like a lighthouse beam focused into an intensely narrow shaft of light. If that tightly collimated radio beam isn't pointed directly at Earth, we wouldn't see the burst at all. But for the counterparts, the picture is different. The lower energy processes that might produce visible light or X-rays could be radiating in all directions, like the general glow from the lighthouse lamp itself. If the beam is narrow, that general glow would be inherently much fainter and could easily fall below the detection threshold of our telescopes, especially across billions of light years. Another possibility is that the environment around the FRB source is so extreme that it effectively absorbs or blocks light at other wavelengths before it can escape. A thick cocoon of dense plasma or debris could act like a one-way mirror, allowing radio waves to pass through but trapping or scattering higher energy radiation. The profound significance of this multi-messenger missing persons case is that it leaves astronomers with a profoundly incomplete picture. Without seeing the event in other types of light, it's incredibly difficult to rule out competing theories or to understand the full physics of the explosion. This search is a cornerstone of modern time domain astronomy, where the global scientific community operates as a single, coordinated instrument. The moment an alert goes out from a radio telescope like CHIME or ASCAP, a pre-programmed network of partner observatories automatically slews into position, some within mere seconds, to capture any potential afterglow or simultaneous flash. The few rare instances where a counterpart has been detected are therefore monumental. The galactic Magnetar burst, FRB 2428, was a landmark event precisely because it did come with a bright X-ray counterpart, finally providing the direct multi-wavelength link that had been so elusive for extragalactic bursts. These successes, however, only deepen the mystery for the vast majority of bursts that remain radio-only events. It suggests that while magnetars are certainly one source, they may not be the only source, and that other, more exotic engines might operate by different rules, conserving their energy for a spectacular but invisible radio performance. The search for these missing counterparts is more than just a technical challenge. It is a fundamental exploration into the efficiency and strangeness of cosmic physics, a quest to see the full spectrum of a phenomenon that so far prefers to whisper in only one language. If the source of these bursts were something straightforward, like the final act of a specific type of star, you would expect to find them only in a specific type of neighborhood, a certain class of galaxy with the right stellar demographics. But the universe, in its infinite creativity, has refused to provide such a simple answer. Instead, the host galaxies of fast radio bursts present us with a bewildering lack of pattern, a cosmic scatterplot that defies easy categorization and challenges our desire for neat astrophysical families. This is the mystery of host galaxy diversity, and it suggests that whatever is creating these immense energies is not a picky tenant. It can set up shop in almost any galactic environment imaginable. The first host galaxy to be identified for the repeater 121102 was a tiny, faint dwarf galaxy. This was intriguing but somewhat expected. Dwarf galaxies are often thought of as cosmic relics, small and primitive, still undergoing intense bouts of star formation. Their simple, chaotic environments are perfect breeding grounds for massive, short-lived stars that end their lives as neutron stars and black holes. Finding an FRB here seemed to fit a neat narrative, a young Magnetar, fresh from a supernova, flashing powerfully from its stellar nursery. It pointed toward a source that was linked to recent, violent stellar birth. But then, other localized FRBs began to tell a completely different story. The next ones to be pinpointed were found not in tiny dwarfs, but in massive, grand design spiral galaxies, much like our own Milky Way. These are mature, well-ordered cities of stars, where the frantic pace of star formation has largely settled down. The FRBs in these galaxies were not always located in the busy, glowing spiral arms where new stars are born. Some were found out in the quieter galactic suburbs, the stellar halos, far from the hustle and bustle of recent supernova. This immediately complicated the picture. It suggested that the engines powering FRBs could also be older, more settled objects, perhaps magnetars that had been around for millions of years and had drifted away from their birthplaces. Or it opened the door to entirely different sources that have nothing to do with young stars at all. The catalogue has only grown more diverse from there. We now have FRBs originating from the hearts of giant elliptical galaxies, colossal spheres of ancient red stars that are essentially retirement communities for suns where star formation ceased eons ago. We have bursts coming from galaxies that are merging, their structures distorted by violent gravitational interactions, sparking new waves of stellar creation. There seems to be no common thread, no single galactic recipe, size, mass, age, or star formation rate that predicts an FRB's home. A brilliant millisecond flash can erupt from a primordial dwarf galaxy barely held together by gravity or from the well-behaved disk of a cosmic titan. This astonishing diversity is actually one of the most critical clues we have, because it forces a profound reconsideration of what an FRB source must be. The fact that they can occur in such wildly different environments tells us that the central engine is likely a very common product of stellar evolution. It can't be something exceedingly rare that only happens under perfect, specific conditions. Instead, it must be an outcome that can occur across a vast range of cosmic times and places. This strongly supports the idea that the source is a neutron star, specifically a magnetar. Neutron stars are created in the supernova explosions of massive stars, and massive stars are born and die in every type of galaxy we know. From the youthful dwarfs to the aging spirals, the population of neutron stars is ubiquitous. The mechanism that triggers the burst, whether a starquake or some kind of magnetic reconnection, might therefore be a universal property of these ultra-dense objects, something that can happen throughout their long lifetimes and in any neighborhood they find themselves in. The host galaxy mystery doesn't simplify the story, but it powerfully narrows the field of suspects to those that are common enough to appear everywhere we look. While the population of fast radio bursts seemed to be growing more diverse and mysterious with each new detection, one source stood out from the very beginning as a true cosmic eccentric. This is the curious case of FRB 121102, the original repeater and arguably the most important object in the entire FRB catalogue. Its story begins not with a single shout, but with a persistent, chattering series of whispers that refused to be ignored. Discovered in 2015 by the Arecibo Radio Telescope, this wasn't a one-off event. It was a source that flickered back to life again and again, sometimes in a flurry of activity, other times falling silent for months. This repetition was the first major clue that forever changed the game, proving that at least some FRBs came from a source that could survive its own outburst. But the true depth of its strangeness was only revealed when astronomers finally managed to pinpoint its home. After a painstaking campaign of observation, its location was traced to a tiny, faint dwarf galaxy more than 3 billion light-years away. This in itself was significant, but it was the specific neighborhood within that galaxy that raised eyebrows. FRB 121102 wasn't just anywhere. It was nestled in a region of extreme star formation, a stellar nursery bursting with the energy of young, massive stars living fast and dying young. This immediately suggested a link between the FRB and a young, energetic object, something recently born from the cosmic chaos of a supernova. The most logical candidate was a magnetar, a highly magnetic neutron star that could theoretically produce repeated bursts through starquakes or magnetic eruptions. But just as that theory was gaining traction, another layer of mystery emerged. When astronomers pointed other radio telescopes at this exact spot, they found something no other FRB source had: a persistent, steady glow of radio radiation. Even when the millisecond bursts themselves were not active, this faint radio source was always there, humming quietly in the background. This was unprecedented. It meant that the environment around FRB 121102 wasn't just occasionally explosive, it was perpetually energized. This persistent radio source became the center of a heated debate. What could possibly be powering this continuous output? One compelling theory is that the FRB source is a very young magnetar, so newborn that it is still embedded within the expanding shell of its own supernova remnant. This hot, dense cloud of debris would glow brightly in radio waves as it expands and interacts with the surrounding interstellar material, providing the steady background hum. The occasional FRB would then be the magnetar's spectacular tantrums from within its glowing crib. However, another, far more exotic idea was put forward. Perhaps the source wasn't a magnetar at all, but something on an entirely different scale. Some scientists proposed that the persistent emission and the repeating bursts could be explained by an active galactic nucleus, a supermassive black hole at the galaxy's center, greedily accreting material and shooting out powerful jets. In this scenario, the FRBs could be produced within these relativistic jets. While intriguing, this theory faced a major challenge. The host galaxy of FRB 121102 is a diminutive dwarf, and such small galaxies aren't typically known for hosting massive, active black holes. It would require a somewhat unusual object, a so-called intermediate mass black hole, making the explanation possible but far less common than the Magnetar model. To this day, FRB 121102 remains a captivating outlier. It possesses a combination of traits: repetition, a star-forming host, and a persistent radio source that, while some have been seen individually in other bursts, have never been found together again in quite the same way. It is the prototype that broke the mold, the first of its kind that still stubbornly refuses to be fully categorized. It taught us that repetition was possible and that environments matter, but it also left us with more questions than answers. Is it a standard example of a young magnetar in a nursery, and we just haven't found enough like it yet? Or is it a truly rare cosmic hybrid, a one-in-a-billion object that operates by its own unique rules? Its enduring mystery serves as a powerful reminder that in astronomy, the first clue is often the most complex, a beacon that illuminates the path forward while stubbornly guarding the deepest secrets of its own nature. Just when astronomers thought the repeating bursts had introduced enough complexity, the universe unveiled yet another baffling layer to the mystery. For years, the repetition from sources like 121102 seemed random, a series of unpredictable cosmic hiccups with no discernible schedule. But then, as more and more repeating FRBs were discovered and monitored over long periods, a strange and tantalizing pattern began to emerge from the noise. Some of these sources weren't just repeating randomly, they were following a strict, almost metronomic clock. This discovery of periodic activity shattered the notion of a purely chaotic engine and introduced a profound new puzzle. What kind of cosmic object operates on a precise, repeating cycle of energetic outbursts and absolute silence, with each cycle lasting for dozens of days? The first major clue came from none other than that original repeater, 121102. After years of monitoring its chattering bursts, researchers noticed something extraordinary. The source wasn't just active all the time, it seemed to follow a rough cycle. It would enter our active window, firing off frequent bursts for about 90 days, and then it would fall completely silent for a subsequent period of roughly 67 days, creating a total cycle of around 157 days. This wasn't a perfect, clean rhythm. The bursts within the active window were still sporadic, but the overall on/off pattern was undeniable. Then, other repeaters began to show even more precise clocks. One source, FRB 189-16.11, was found to have a remarkably strict period of 16.33 days. For 12.4 days, it remains completely silent. Then, for a window of approximately 3.9 days, it can and does burst, lighting up our telescopes before going quiet again for another 12 days. This isn't a suggestion of a pattern. It's a precise, predictable schedule written into the fabric of the cosmos. This kind of periodic behavior is a gift to theorists because it immediately points toward a physical mechanism involving orbital motion or rotation. In astrophysics, a stable, repeating clock is almost always the signature of an object moving in a gravitational dance. The most straightforward explanation is that the FRB source is not a single, isolated object, but one part of a binary system. Two objects locked in orbit around a common center of gravity. Imagine a scenario where the engine of the burst is a highly magnetized neutron star, and it's orbiting another, much larger body, perhaps a massive star or even a black hole. The cycle of activity and silence could be tied directly to its position in this orbit. Perhaps the companion star has a strong stellar wind or is surrounded by a thick disk of gas and dust. The FRB might only be visible to us or only be triggered when the neutron star is at a specific point in its orbit, when it plunges through this dense material, which then acts as a trigger or a lens for the emission. During the rest of the orbit, the source is either physically obscured by the companion or simply not in the right environment to produce a burst we can detect. Another compelling model involves the complex physics of a spinning neutron star itself, specifically a phenomenon known as precession. Much like a wobbling top that slowly traces a circle as it spins, a neutron star can also wobble if its rotation axis is not perfectly aligned with its magnetic axis. This slow, graceful wobble is called precession, and its cycle can take weeks or months to complete. In this model, the incredibly powerful beam of radio emission generated by the star is like a lighthouse beam that doesn't just rotate, but also slowly wobbles across the sky. For a period of time during this precession cycle, that intense beam is pointed directly at Earth, and we see that as the active window detecting multiple bursts. Then, as the wobble continues, the beam drifts away from our line of sight, and the source enters its silent period, even though the engine itself might still be firing. The beam is just aimed away from us, sweeping across other parts of the galaxy until its cycle brings it back our way. These periodic patterns add an immense layer of complexity to the FRB enigma. They provide a crucial new constraint for any viable theory, demanding that it account not only for the prodigious energy output but also for a stable, long-term clockwork mechanism. The period itself becomes a direct measurement we can use to understand the system, the orbital period in a binary model, or the precession period in a solo model. With each new repeating FRB that exhibits a cycle, we get another data point, another clock to compare, helping us to determine if this is a universal behavior or one that comes in several flavors. The mystery of periodic activity transforms these bursts from mere explosions into characters in a cosmic ballet, their movements choreographed by the fundamental forces of gravity and rotation, revealing a depth of structure we are only just beginning to decode. Beyond their timing and energy, the very nature of the radio waves themselves holds a crucial key to unlocking the environments they traverse. This brings us to the intricate polarization puzzle, a subtle but powerful property of light that allows us to map the invisible magnetic fields of the cosmos. To understand this, picture a radio wave not just as a wave of energy, but as a wave that vibrates in a specific direction. This preferred direction of vibration is what we call polarization. Now imagine that this polarized wave travels through a region of space filled with a magnetized plasma, a hot soup of charged particles threaded with magnetic fields. As it does so, something remarkable happens. The direction of its vibration slowly rotates, a phenomenon known as Faraday rotation. The degree of this rotation is directly proportional to the strength of the magnetic field along the path and the density of electrons it encounters. By meticulously measuring this twist, astronomers can calculate what's known as the rotation measure, a single number that acts as a direct probe of the integrated magnetic field strength between us and the source. For most cosmic radio sources, like distant galaxies or quasars, the rotation measure is a relatively stable value. It might change slowly over years as the source evolves, but it generally provides a consistent reading of the magnetic environment. With fast radio bursts, however, the data tells a dramatically different and far more volatile story. When astronomers have been able to measure the polarization of repeating bursts from the same source, they have observed something astonishing. The rotation measure can be wildly variable, sometimes flipping sign or changing by enormous amounts between one burst and the next, even when those bursts are separated by only a few hours or days. This isn't a slow, gradual shift. It's a sign of a magnetic environment in a state of violent, turbulent upheaval. Such extreme and rapid variability places the source of this magnetic chaos incredibly close to the FRB engine itself. The magnetic fields between galaxies are vast and diffuse, and they simply cannot change on such short timescales. It would be like the entire Pacific Ocean changing its current in a matter of minutes. The only plausible explanation is that this Faraday rotation is occurring in a dense, highly magnetized region immediately surrounding the progenitor. The magnetic fields in this local environment must be mind-bogglingly intense and dynamically evolving. We are likely talking about a supernova remnant so young and energetic that its expanding shockwave is still plowing through the interstellar medium, or the powerful magnetosphere of a neutron star where magnetic field lines are constantly snapping and reconnecting, releasing immense energy. Each new burst from a repeater effectively takes a fresh snapshot of this chaotic magnetic storm, allowing us to witness its evolution in near real time and giving us an unprecedented front row seat to some of the most extreme physics in the universe. If the timing and polarization of these signals offer clues about their journey and environment, the very fabric of the signal itself, its spread across the radio dial, holds another profound puzzle. This is the bandwidth conundrum, a mystery that asks why these bursts don't all sound the same. When we tune our radio telescopes across the sky, we don't listen to a single frequency. We open a wide window, scanning a broad spectrum of channels simultaneously, much like turning a dial across an entire radio band. The range of frequencies over which a signal is detected is its bandwidth, and for fast radio bursts, this property varies wildly from one event to another, presenting a dazzling and confusing diversity. Some bursts are like precision instruments, emitting a sharp, laser-like signal concentrated within a very narrow slice of the radio spectrum, sometimes as tight as just a few tens of megahertz. These narrowband bursts suggest an emission process that is incredibly fine-tuned and efficient, perhaps originating from a very specific, coherent mechanism within a highly ordered environment. Then, in stark contrast, there are the spectacular wideband bursts that blast their signal across a staggering range, from a few hundred megahertz all the way up to several gigahertz. These are the cosmic broad-spectrum shouters, flooding the radio waves with their presence. This vast difference in bandwidth isn't a minor technical detail. It is a direct fingerprint of the underlying physics, pointing toward fundamentally different ways for nature to generate these immense flashes of radio light. The width of a burst tells a story about the environment it was born in and the mechanism that created it. A very narrow bandwidth can be a sign of a process called maser emission, a natural amplification of radio waves that occurs under very specific conditions within a dense magnetized plasma. It's a coherent process where the waves are all perfectly in sync, resulting in a very pure single-frequency tone. This could happen in the intense magnetosphere of a neutron star, where powerful magnetic fields can force radiation into a very specific narrow band. On the other hand, an extremely wide-band burst suggests an impulsive, incoherent process, a sudden, violent release of energy that generates a chaotic fireball of radiation across all frequencies at once, like the electromagnetic equivalent of a shockwave from an explosion. The broadest bursts could be caused by a cataclysmic event that instantly accelerates a vast sea of particles to near light speed within a magnetized plasma, creating a brilliant flash that contains every radio color at once. Furthermore, the journey itself can sculpt the signal's bandwidth. A burst might start as wideband at its source, but if it has to travel through a dense, cloudy environment full of free electrons, the lower frequencies can be delayed and scattered more than the higher ones. This process can smear the signal out in time and frequency, potentially making it appear narrower by the time it reaches us, as the leading and trailing edges of the different frequencies get muddled together. Alternatively, an effect called plasma lensing, where dense clumps of material in space act like a lens, could temporarily focus the radio waves, amplifying certain frequencies and making the burst appear both brighter and potentially narrower in bandwidth for a brief moment. The bandwidth we measure is therefore not always a pure reflection of the source. It can be a distorted echo, reshaped by the cosmic terrain it had to cross. This conundrum forces astronomers to become cosmic detectives, carefully disentangling the intrinsic properties of the burst from the propagation effects imposed by its long journey, all in an effort to hear the true voice of the engine that shouted into the dark. But the peculiarities of these signals don't end with their timing or polarization. Some repeating bursts exhibit an even more whimsical and specific behavior, a bizarre auditory fingerprint that has astronomers utterly captivated. This is the frequency drift phenomenon, a characteristic that makes these cosmic events sound less like a static burst and more like a slide whistle played across the universe. When we break down the structure of a complex FRB from a repeater, we often find that it's not a single monolithic pulse. Instead, it can be composed of several smaller subbursts, each one a tiny packet of radio energy. And in many cases, these subbursts don't all sound the same note. With astonishing regularity, each subsequent subburst within a single event is emitted at a slightly lower frequency than the one that came before it. The entire sequence drifts downward in pitch over a few milliseconds, creating a distinctive falling tone effect, as if some cosmic musician were running a finger down the spine of a radio-scale xylophone. This downward drift is not just a curious oddity, it is a profound clue etched into the very fabric of the signal, a direct tracer of the extreme physics at play. To generate such a clean and consistent shift, the environment around the source must be doing something highly organized and predictable. One of the leading theories points to the complex dynamics within the magnetosphere of a neutron star. Imagine the source of each subburst is not stationary but is actually moving. Picture a spark of energy igniting at a particular point high in the magnetosphere, where the magnetic field lines are incredibly dense. The radio waves generated there would naturally be at a very high frequency. As the spark evolves or the shock wave from the initial energy release propagates outward, it travels along these curved magnetic field lines, moving away from the star's surface and into regions where the magnetic field strength naturally weakens. The frequency of radio emission in such an environment is directly tied to the local magnetic field strength. So as the source plunges into a weaker field, the frequency of the radio waves it produces drifts lower and lower. Each subburst could represent a new spark following the same path, each one starting its journey a fraction later and therefore emitting its highest frequency at a slightly lower starting point, creating that beautiful stepped downward drift. An alternative and equally fascinating explanation involves not the source itself moving, but the signal traveling through a strange and volatile cosmic lens. This theory invokes a process called plasma lensing. Between us and the FRB source, there could be dense, cloudy clumps of plasma-ionized gas floating in space. As the broad-spectrum radio waves from the burst pass through these clumps, something remarkable happens. The plasma acts like a lens, but one that works differently for different colors of radio light. It can briefly focus the waves, making the burst appear brighter, but it can also cause a delay that is frequency dependent. the lower frequency components of the signal might be slightly delayed compared to the higher frequencies as they navigate this turbulent plasma. If the properties of this plasma cloud are changing rapidly during the few milliseconds of the burst, perhaps due to the incredible energy of the blast itself, it could create the illusion of a downward frequency drift. The later subbursts would have their lower frequencies progressively more delayed, making it seem as if the pitch was falling over time. This would mean the drift isn't intrinsic to the source at all, but is instead a signature of the signal's passage through a stormy sea of particles, a final cosmic filter that adds its own unique twist to the message before it reaches our telescopes. The frequency drift phenomenon, whether caused by a moving source within a colossal magnetosphere or by the distorting effects of a plasma lens, provides a stunningly detailed window into the microphysics of these events, allowing us to almost hear the machinery of the cosmos operating in real time. While the discovery of repeating bursts was a revolution in itself, a new class of repeater has since emerged that pushes the boundaries of what we thought was possible. These are the hyperactive repeaters, sources that don't just occasionally whisper back to us, but instead unleash a veritable torrent of radio energy, sometimes firing off hundreds of detectable bursts in a single day. This isn't a slow, sporadic conversation with the cosmos. It's a frantic, non-stop barrage that challenges our very notion of what a stable cosmic engine can look like. The existence of such prolific sources forces us to confront a critical question. How can an object survive such relentless self-cannibalization without tearing itself apart? Consider the energy budget required. Each individual burst, as we've established, represents a staggering release of power. For a source to produce hundreds of these events, it must have access to an energy reservoir of almost unimaginable scale or possess a mechanism that is astoundingly efficient. Cataclysmic, one-time events are completely ruled out. You cannot have hundreds of supernova from the same star. Even the standard Magnetar starquake model begins to strain under the pressure. While a magnetar's magnetic field is an immense source of energy, frequent, powerful crustal fractures would presumably settle down over time as the stresses are released. A source that maintains a high burst rate for months or years suggests an engine that isn't winding down, but is instead being persistently fed or triggered by its environment. This hyperactive behavior points toward an engine that is not only stable but also capable of rapid recharge. One compelling idea is that we are witnessing a magnetar that is unusually young and active, perhaps still enshrouded in the hyper-energetic debris of its birth supernova. In this tumultuous nursery, the star could be continuously bombarded by infalling material from its surroundings, each impact triggering a new magnetic reconnection event and a subsequent FRB. Another fascinating possibility involves a binary system where the neutron star is actively accreting matter from a companion star. As gas from the donor star spirals onto the magnetar's surface, it could introduce fresh instabilities into the already intense magnetic field, sparking bursts in a continuous cycle of consumption and eruption. In this scenario, the accretion process itself provides the fuel, turning the FRB source into a kind of cosmic pressure valve that releases energy as fast as it builds up. The most extreme example of this is the remarkable source FRB 2020-90's 514. For a period of 47 days, this object was monitored, producing an average of nearly 120 bursts per hour. At its peak, it was firing more than 3 times per minute. This isn't just an active source, it's a radio machine gun operating with a ferocious consistency that defies simple analogy. Such a high rate of production suggests that the triggering mechanism cannot be a large-scale, destructive event. Instead, it must be a relatively small, localized process that can occur over and over again across the surface or magnetosphere of the object without causing its overall structure to fail. It implies that the burst we see is merely the tip of the iceberg, the brightest manifestation of a continuous, underlying storm of activity that is always happening, only occasionally directing a beam of coherent radio waves in our direction. Studying these high-rate repeaters offers a unique advantage: statistical power. With hundreds or thousands of bursts from a single source, astronomers can perform detailed analyses that are impossible with one-off events. They can study the distribution of energies, the wait times between bursts, and the clustering of activity, searching for patterns that might reveal the underlying physics. Some sources show signs of Poisson statistics, truly random arrival times, suggesting a process driven by turbulent, unpredictable instabilities. Others hint at more complex patterns, with bursts clustering together, which could indicate that one burst triggers another in a domino effect across the star's magnetic field. Each new hyperactive repeater discovered adds another data set to this growing field of statistical seismology, allowing us to probe the inner workings of these engines not through a single snapshot, but through a long-term, high-resolution movie of their explosive lives. Their relentless activity is a gift that keeps on giving, providing the raw data we need to finally understand the ticking heart of the most persistent mysteries in the universe. As we amass an ever-growing catalog of these cosmic signals, a fascinating and potentially revolutionary pattern begins to emerge from the data, one that suggests the universe might be employing not one, but two distinct blueprints for its most powerful radio flashes. This is the compelling evidence for a bimodal distribution, a statistical split in the properties of fast radio bursts that hints at a fundamental duality in their origins. When you plot key characteristics like dispersion measure or burst width against each other, the points don't form a single, smooth cloud. Instead, they often cluster into two separate groups, as if nature itself is drawing a line between two different families of phenomena. This isn't a subtle trend, it's a glaring division in the data that demands an explanation. The most striking split appears along the axis of repetition itself. On one side, we have the large population of apparently one-off bursts. These events tend to have higher dispersion measures on average, suggesting they come from further away, and their single, catastrophic flash points toward a source that is destroyed in the process. On the other side, we have the growing family of repeating FRBs. These often, though not always, show lower dispersion measures, indicating somewhat closer proximity, and their very existence proves their source is a persistent engine. This clean division initially suggested a simple, binary answer. Perhaps the non-repeaters are the final death cries of merging neutron stars or collapsing black holes, violent and singular events, while the repeaters are the tantrums of young, stable magnetars, capable of firing again and again. It was a beautifully elegant solution, but the universe rarely adheres to our desire for neat categories. The plot thickens considerably when we realize that the distinction might not be so absolute. The discovery of a small number of sources that initially appeared as one-off events, only to burst again months or even years later, throws a wrench into this simple binary. Furthermore, some repeaters can produce bursts that are incredibly energetic, rivaling the power of the one-off events, blurring the energy boundary between the two groups. This forces us to ask a critical question. Are we truly seeing two separate cosmic production lines, or are we witnessing a continuum of behavior from a single type of object, with our observations being heavily skewed by perspective and bias? The case for observational bias is surprisingly strong. Consider the challenge of detection. A repeater that is relatively inactive, firing only a few times a year, is incredibly easy to miss. If our telescopes aren't pointing at that precise patch of sky during its brief moments of activity, we would catalog it as a one-off event. Its true, repeating nature would remain hidden, artificially inflating the number of apparent non-repeaters. Conversely, a one-off event is by definition a single chance detection. We have no opportunity to go back and study it further, to measure its rotation, measure variability, or pinpoint its host galaxy with the same precision we can with a repeater. This fundamental difference in how we can observe each type creates a selection effect that can easily exaggerate the differences between them in our catalogs, making them appear more distinct than they might actually be. Yet, even after accounting for these biases, the statistical evidence for two populations remains stubbornly persuasive for many astronomers. The clustering in the data is real. This leads to the profound implication that there may indeed be two fundamentally different types of progenitors at work. One progenitor could be a catastrophic event, a true cosmic suicide packed like a binary neutron-star merger, which creates a brilliant final flash and accounts for the one-off population. The other progenitor would be a stable but periodically unstable object like a magnetar, which can experience multiple eruptions throughout its long life, accounting for the repeaters. In this two-progenitor model, the universe is telling us that it has at least two wildly different, yet equally effective, ways to generate these astonishing bursts of energy. The resolution to this mystery holds the key to understanding the entire FRB phenomenon. If the distribution is truly bimodal, it means we are dealing with two separate astrophysical puzzles to solve, each with its own set of rules and implications for stellar evolution and cosmic physics. If, however, it is a continuum shaped by observation and environment, it points toward a single, incredibly versatile engine like a magnetar that can operate in a variety of modes, from producing isolated, super-powerful outbursts to frequent, weaker hiccups, depending on its age, magnetic field configuration, and surrounding environment. This isn't just an academic debate over statistics. It's a fundamental inquiry into the diversity of physical mechanisms that shape our universe, forcing us to look ever deeper into the data to hear what the cosmos is truly trying to say. While we've been marveling at the incredible energy and mysterious patterns of these bursts across common radio frequencies, there's a significant part of the radio spectrum that remains eerily quiet in the FRB story. This is the mystery of the missing low-frequency FRBs. Our most sensitive radio telescopes are capable of listening to a vast symphony of cosmic static, from the high-pitched gigahertz shrieks down to the deep, rumbling megahertz tones. According to our basic understanding of how radio emission works, a powerful, broad-spectrum explosion should theoretically blast its signal across this entire range. We should be detecting these events just as easily at 300 MHz as we do at 1.4 GHz, but the observational data tells a completely different and rather baffling tale. Below a threshold of around 400 MHz, the number of detected fast radio bursts falls off a cliff. They become exceedingly rare, almost to the point of non-existence. This isn't for a lack of trying. Dedicated low-frequency arrays like LOFAR in Europe and the MWA in Australia are constantly scanning the skies, listening to these deeper cosmic notes. They detect plenty of other phenomena, pulsars, Jupiter's storms, distant galaxies, but the brilliant milliseconds-long flashes that are so common at higher frequencies simply don't show up in their data with any regularity. It's as if a cosmic filter is placed over the universe, selectively blocking these specific signals from reaching us at lower pitches. This absence forms a clear and puzzling lower boundary to the FRB phenomenon, a cutoff that shouldn't exist if the emission process were as simple as we once thought. So, what is silencing these cosmic shouts at lower frequencies? Scientists are investigating several compelling possibilities, each pointing to a different part of the journey from source to telescope. The first and most likely culprit is a propagation effect called scattering. As a radio signal travels through the sea of free electrons that permeate space, it doesn't just get dispersed, it can also get smeared out. This scattering is caused by the signal encountering turbulent, clumpy clouds of plasma. The effect is wildly dependent on frequency. Lower frequency waves are scattered and delayed far more dramatically than their higher frequency counterparts. For a signal originating billions of light years away, the cumulative scattering at very low frequencies could be so severe that an originally millisecond-long burst is stretched out into a faint, seconds-long wash of static. This would dilute its intensity, making it blend seamlessly into the background noise of the universe and effectively rendering it invisible to our detectors. The burst is still there, but its sharp, recognizable spike has been erased by its long journey. Another potential explanation lies in simple absorption. The signal might be getting literally soaked up along the way. If an FRB's path to Earth takes it through a particularly dense and ionized region of space, like the halo of hot gas surrounding its own host galaxy or a dense nebula near the source, that material could act like a cosmic sponge, absorbing the lower frequency radio waves before they can escape into intergalactic space. This is similar to how Earth's ionosphere reflects low-frequency radio waves, allowing for long-distance AM radio communication, but also blocking those same frequencies from reaching ground-based telescopes pointed at space. The source could be firing brilliantly in all directions, but if it's trapped inside a dense cocoon of plasma, we might only ever see the high-frequency component that manages to punch its way through. A third and far more intriguing possibility is that the cutoff isn't due to the environment at all, but is intrinsic to the emission mechanism itself. Perhaps the physics that generates an FRB simply doesn't produce significant radiation below a certain frequency. This would be a monumental clue pointing directly to the specific nature of the engine. Certain coherent emission processes, like those thought to occur in the magnetospheres of neutron stars, have a natural plasma frequency cutoff. This is the minimum frequency that can propagate through a dense plasma. Any radiation below that frequency is effectively suppressed at the source. If the FRB is born in an extremely dense environment, like the base of a magnetar's magnetosphere, its radio voice might be naturally muted at the lower end, only becoming loud and clear above a specific threshold. Discovering this intrinsic cutoff would be like finding the operating manual for the engine, telling us the precise density and magnetic conditions where it must be forming. The search for low-frequency FRBs is more than just an attempt to fill a gap in our charts. It's a critical diagnostic tool. Every non-detection helps us rule out certain models and refine others. Finding even a handful of clear, low-frequency bursts would be a watershed moment, providing crucial data to measure the scattering along their path and finally map the truly faint and elusive material that exists in the vast voids between galaxies. This quiet corner of the radio spectrum holds the key to understanding the final leg of the FRB's journey and the exact nature of the cosmic cradle in which it was born. For years, the search for the source of fast radio bursts was a hunt for ghosts in the deep cosmic dark, a puzzle built on signals that had traveled billions of light years. All the evidence was indirect, all the theories untested. That all changed spectacularly in April 2020, when the universe delivered a cosmic gift to our very own galactic doorstep. The source was a known object within the Milky Way, a magnetar named SGR 1935+2154, located a mere 30,000 light-years away. For days, this highly magnetic neutron star had been in a state of violent upheaval, emitting a series of intense X-ray and gamma-ray flares. Then, on April 28th, as it let out one particularly strong X-ray cry, something unprecedented happened. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and the Survey for Transient Astronomical Radio Emission 2, or STARE-2, detected an immensely bright, millisecond-long radio burst erupting from the exact same location at the exact same time. This was FRB 2004-28, and it was the first ever fast radio burst detected from within our galaxy. The discovery was nothing short of seismic for the astronomy community. It was the smoking gun, the direct observational link that had been sought for over a decade. Here, finally, was concrete proof that a magnetar, a super-dense, highly magnetized neutron star, was capable of producing a fast radio burst. The event confirmed the core premise of one of the leading theories, that the incredible magnetic stresses on a magnetar can trigger a starquake or a massive magnetic reconnection event, releasing a torrent of energy that manifests as a brilliant flash of radio waves. This single detection from a known object in our cosmic backyard validated years of work and instantly made the Magnetar model the frontrunner for explaining at least a significant portion of the FRB population. Yet, in classic scientific fashion, this answer immediately raised a host of new and even more perplexing questions. The most glaring was the energy problem. The galactic FRB from SGR 1935 plus 2154 was certainly powerful, but it was a faint whisper compared to its extragalactic cousins. It was orders of magnitude less energetic than the bursts we detect from galaxies billions of light-years away. If this Magnetar burst is the template, then how do we explain FRBs that are thousands of times more powerful? It suggests that the magnetars in distant galaxies must be capable of outbursts far more violent than anything we have witnessed in our own. Perhaps they are younger, more magnetically potent, or situated in environments that somehow amplify their output. Maybe they are triggered by external factors, like the infall of material from a companion star, supercharging the eruption. This energy discrepancy forces us to consider whether the Magnetar model is a complete picture. Does it explain all FRBs or just a certain class? The detection from within our galaxy proved that magnetars can produce FRBs, but it did not prove that they are the only things that can produce them. It leaves the door wide open for the possibility of multiple progenitors. Perhaps the less energetic, repeating bursts are the work of magnetars, while the more energetic, one-off events are still caused by different, even more catastrophic phenomena like neutron star mergers. The galactic FRB was a crucial piece of the puzzle, but it showed us that the full picture is far more complex and magnificent than we had imagined. A reminder that a single answer in science often leads to a universe of new mysteries. The properties of a fast radio burst are like a detailed cosmic passport, stamped with the conditions of every environment it passed through on its journey to Earth. For many of these signals, that passport reveals a history of transit through some of the most extreme and violent neighborhoods in the universe. The clues are etched into the radio waves themselves, their intense scattering, their high dispersion measure, and their wildly variable polarization all point toward an origin within a maelstrom of dense plasma and unimaginably powerful magnetic fields. This isn't the calm, sparse void of deep intergalactic space. This is a region of chaos, a cosmic pressure cooker where the normal rules of physics are stretched to their absolute limit. Inferring the nature of these extreme environments is like being a forensic scientist at the scene of a cosmic explosion, using the scattered fragments of evidence to reconstruct the event itself and the conditions that made it possible. So, what does such an environment actually look like? The evidence strongly suggests we are peering into the aftermath of stellar death, into the dynamic and short-lived structures created when the most massive stars exhaust their fuel. The prime suspect is a young supernova remnant, the expanding shell of debris blasted outward from a colossal stellar explosion. For thousands of years after the supernova, this remnant is a turbulent, expanding cloud of hot, ionized gas, a perfect plasma, laced with intense magnetic fields that were amplified and tangled in the violence of the blast. Any signal emanating from within this shroud would have to fight its way out, its radio waves scattered and delayed by the dense, chaotic material. This explains why some FRBs show such strong scattering tails. They are the echoes of a journey through a storm of stellar debris. Furthermore, if the source of the burst is the neutron star left behind by the supernova, a magnetar, then it is a newborn residing in its own messy cradle, its powerful outburst shaped by the very environment its birth created. The presence of strong magnetic fields is another telltale signature of an extreme environment. The rapid and dramatic changes in the rotation measure observed in some repeating FRBs point to a magnetic landscape that is not just strong but dynamically evolving. The magnetic fields in these regions must be intense enough to influence the very structure of atoms and powerful enough to undergo sudden reconfigurations, events known as magnetic reconnection, which can release catastrophic amounts of energy almost instantaneously. This is the domain of the Magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's. The environment within a magnetar's magnetosphere is so extreme that it can support starquakes ruptures in the star's rigid, crystalline crust that release more energy than a magnitude 32 earthquake. Each quake sends a shock wave through the surrounding magnetosphere, accelerating particles and triggering the coherent radio emission we see as a burst. The Magnetar doesn't just exist in an extreme environment. It is the extreme environment, its very existence defining the physics of the space around it. This connection to massive stars tells a profound story about the life cycle of the most dramatic objects in the cosmos. The ability to produce an FRB seems to be a phase, a period of intense youthful activity in the life of a neutron star. A magnetar is born in the fire of a supernova, and for the first several thousand years of its life, it is both incredibly powerful and nestled within the expanding remnant of its progenitor star. During this volatile adolescence, it is prone to these gigantic magnetic outbursts. The FRBs we see from within such environments are the cries of a cosmic infant, powerful but still obscured by the glowing nebula of its birth. As the supernova remnant expands and dissipates over hundreds of thousands of years, the environment around the magnetar gradually clears. The scattering of its signals would lessen, and the bursts might change in character, eventually ceasing as the star's magnetic field slowly decays over millions of years. Therefore, by studying the propagation effects on an FRB, we are not just locating a source, we are essentially carbon dating its environment, determining whether we are witnessing the tantrums of a newborn or the more settled, rarer outbursts of a middle-aged object. The inference of extreme environments extends the significance of FRBs far beyond the bursts themselves. They become powerful probes, brilliant flashlights that we can use to illuminate the otherwise invisible conditions around some of the most exotic objects in the universe. Each new localized FRB gives us a snapshot of a specific moment in the life and death of a massive star. By building a catalog of these events from different types of host galaxies and with different environmental signatures, we are piecing together a grand narrative of stellar evolution's most energetic chapters. We are learning how magnetic fields are forged in stellar explosions, how neutron stars cool and evolve, and how the remnants of dead stars enrich and shape the galaxies they reside in. The mystery of these extreme environments is ultimately a window into the continuous cycle of cosmic death and rebirth, where the end of one massive star provides the turbulent, magnetized cradle for the next generation of cosmic mysteries to be born. Yet for all their potential, this promise of a new cosmic ruler is tempered by a fascinating complication that has emerged from the data. When astronomers began to precisely locate FRBs and independently measure the distance to their host galaxies, they could calculate the expected amount of dispersion, the predicted number of free electrons along that specific line of sight based on our best models of the universe. Time and again, they found a puzzling discrepancy. The actual dispersion measure observed in the FRB signal was often significantly higher than this predicted value. The signal had encountered more electrons on its journey than our maps of the cosmos said should be there. This is not a small accounting error. It is a major clue that a substantial portion of the universe's normal matter, the so-called missing baryon problem, has been hiding in plain sight, or rather in the dark. For decades, cosmologists have faced a conundrum. When they inventory all the normal matter, the protons, neutrons, and electrons that make up stars, planets, and us, that should exist based on observations of the early universe. A significant fraction of it is unaccounted for in the present-day universe. We can see it in the primordial plasma of the Big Bang, but we can't find it all now. This missing matter isn't the mysterious dark matter. It's the ordinary stuff that's just been incredibly difficult to detect because it isn't glowing in stars or cold, dense clouds of gas. The dispersion measure excess found in FRB signals provides the most compelling evidence yet for where this missing material has been hiding. It is tied up in a diffuse, warm-hot intergalactic medium, a vast web of incredibly thin, ionized gas filaments stretching between galaxies. This gas is so hot it emits very little light and so diffuse that it's nearly invisible to all other observational techniques. But to a traveling radio wave, it is a tangible obstacle, a fog that leaves its fingerprint as a delay. Each FRB with a precise location acts like a single probe sent into this cosmic web, and by collecting hundreds of them, we can begin to build a three-dimensional map of this invisible structure, weighing the universe's missing matter for the first time. This dual role, as both a precise measurement tool and a revealer of profound cosmic anomalies, is what makes the cosmological promise of fast radio bursts so extraordinary. They are not just passive yardsticks, they are dynamic explorers, illuminating the dark, empty spaces between galaxies and showing us that they are not empty at all, but filled with a delicate and intricate architecture of warm gas that holds the final pieces of our universal inventory. With every new burst detected and localized, we add another point to this emerging map, slowly tracing the hidden skeleton of the cosmos and turning one of astronomy's greatest frustrations into a thrilling new frontier of discovery. Yet the polarization of these radio whispers holds an even more specific secret, one that allows us to map the invisible magnetic architecture of the cosmos with startling precision. This is the enigma of Faraday rotation, a subtle but powerful effect that twists the very orientation of a radio wave as it journeys through magnetized space. To visualize this, think of polarized light not just as a wave, but as a wave that vibrates in a specific plane, like a rope being shaken up and down. Now imagine that rope passing through a region filled with a magnetic field and ionized gas, a plasma. The interaction between the wave and this magnetized plasma causes the plane of vibration to slowly rotate like a dial being turned. This is Faraday rotation, and the degree of this twist is a direct and quantifiable measure of the magnetic field strength integrated along the entire path the light has traveled. It gives astronomers a single, crucial number known as the rotation measure, a value that essentially sums up the total magnetic push the signal endured on its billion light-year voyage. For most cosmic radio sources, this rotation measure is a stable, predictable number. It might change slowly over millennia as a galaxy evolves, but it acts as a consistent fingerprint of a relatively calm magnetic environment. With fast radio bursts, however, the data reveals a picture of sheer magnetic pandemonium. When astronomers have measured the polarization of repeating bursts from the same source, they have been astonished to find that the rotation measure can be not just high, but wildly variable. It can swing by enormous amounts, sometimes even flipping its sign completely between one burst and the next. These aren't slow, glacial changes. We're talking about drastic shifts occurring over a matter of hours or days. Such extreme volatility is the hallmark of an environment in a state of ferocious, real-time upheaval, a magnetic storm of almost unimaginable intensity. The breathtaking speed of these changes is the most critical clue, and it forces a dramatic conclusion. This Faraday rotation isn't happening in the quiet magnetic fields that drift between galaxies. Those vast intergalactic fields are immense but incredibly weak and diffuse. They are simply incapable of changing on such short timescales. To alter the rotation measure this rapidly, the magnetic chaos must be occurring in a region incredibly close to the FRB source itself. We are likely talking about a zone of space no larger than our own solar system, but one that is filled with a super-dense, violently agitated plasma and threaded with magnetic fields of literally astronomical strength. The only known objects capable of creating such conditions are the aftermaths of stellar cataclysms, perhaps a hyper-young supernova remnant so fresh that its expanding shockwave is still plowing through and electrifying the surrounding medium, or the immediate magnetosphere of a neutron star, where magnetic field lines are constantly snapping and reconnecting with the energy of a million suns. Each new burst from a repeater gives us a fresh snapshot of this ongoing magnetic hurricane, allowing us to witness the microphysics of a cosmic explosion in a way that was previously impossible. The values of the rotation measures themselves are what truly stretch the limits of physics. Some FRBs have been recorded with rotation measures in the tens of thousands of radians per square meter, and a few extreme cases have reached values exceeding 100,000. To provide some context, the rotation measure from a pulsar in our own Milky Way typically measures in the hundreds. The magnetic field strength required to produce the values seen in these extragalactic bursts are almost incomprehensible. They point to environments where the magnetic pressure dominates everything, overwhelming gravity and thermal pressure to dictate the structure and behavior of matter itself. Theorists are now wrestling with how such conditions can naturally arise and be sustained. It suggests that the progenitors of these bursts, likely magnetars, may be even more magnetically potent than our standard models allow, or that they are situated within nebulae of their own creation that act as magnetic amplifiers, concentrating and focusing these incredible fields into a maelstrom that then twists the signals fighting to escape. The Faraday rotation mystery thus does more than just confirm the presence of magnetic fields. It reveals their ultimate expression, showing us a side of the universe where magnetism is not just a force, but the absolute ruler of a realm. If the universe's most powerful radio bursts are truly born from cataclysmic events like neutron star collisions or the collapse of massive stellar cores, we would expect them to announce their arrival with more than just a shout across the radio spectrum. We would anticipate a full-spectrum symphony of violence, with signals arriving through multiple cosmic messengers. Specifically, we would expect to see fast radio bursts arriving hand in hand with two other fundamental signals: a shower of ghostly subatomic particles called neutrinos and the literal ripples in space-time known as gravitational waves. Yet, despite our most diligent searches, this expected cosmic chorus has largely failed to materialize. The profound and puzzling silence from our neutrino and gravitational wave observatories forms our next great mystery, forcing a dramatic reconsideration of just how clean, or perhaps how strange, the FRB engine truly is. Let's first consider neutrinos. These nearly massless particles are famed for their ability to slip through matter almost completely unaffected. Trillions are passing through your body every second without a single interaction. This ghostly nature makes them incredibly difficult to detect, but it also makes them perfect messengers from the hearts of the universe's most violent events. A core collapse supernova, for instance, releases a tremendous blast of neutrinos carrying away the vast majority of the explosion's energy. Our detectors, like the enormous ice cube observatory buried in the Antarctic ice, are finely tuned to catch these rare interactions. If an FRB were produced by a similar cataclysm, a supernova, a hypernova, or the merger of two neutron stars, it should generate a similarly enormous pulse of neutrinos that would reach Earth at nearly the same time as the radio burst. The fact that despite numerous FRB detections, not a single one has been conclusively linked to a coincident neutrino signal is a stunning and telling absence. It suggests that the process creating the FRB is either not producing the expected number of high-energy neutrinos, or it is not the type of event we thought it was. Now turn to gravitational waves, the ripples in the fabric of space-time first predicted by Einstein and finally detected a century later by the LIGO and Virgo observatories. These waves are generated by the accelerated motion of massive objects, most spectacularly by the final inspiral and merger of binary pairs of black holes or neutron stars. The first ever multi-messenger observation of a neutron star merger in 2017 was a landmark event because it included both gravitational waves and a faint flash of light across the electromagnetic spectrum. Given that some leading FRB theories involve these exact same types of mergers, it was only logical to search for a gravitational wave signal coinciding with a fast radio burst. Yet, just like with neutrinos, the searches have come up empty. For the handful of well-localized FRBs that occurred during times when the gravitational wave detectors were operational, no matching ripple in space-time was found. This consistent lack of corroborating evidence from these other cosmic channels is a deafening silence that speaks volumes. It strongly implies that the standard, extremely violent models for FRB production might be missing a crucial piece of the puzzle. A neutron star merger or a core collapse supernova is an incredibly dirty and chaotic event, involving the acceleration of vast amounts of matter to incredible speeds and the production of a wide spectrum of radiation and particles. The fact that we see a brilliantly clean, coherent radio burst without the expected accompanying signals from these other channels suggests that the FRB mechanism might be a far more efficient and focused process. Perhaps the energy release is channeled almost exclusively into accelerating particles along specific magnetic field lines to produce coherent radio emission, with very little energy wasted on the side production of neutrinos or the large-scale bulk motion of mass that would generate detectable gravitational waves. This cleanliness is a hallmark of the Magnetar star-quake model. In this scenario, the energy for the burst comes from a sudden restructuring of the star's unimaginably powerful magnetic field. This magnetic reconnection or crustal fracture event can release a colossal amount of energy, but it does so in a relatively localized and magnetically dominated environment. It doesn't involve the large-scale hydrodynamic chaos of a full star collapse or the inspiral of two massive objects. It's a more precise, almost surgical release of magnetic tension, which could explain why it doesn't generate the broader suite of signals we associate with more catastrophic events. The missing neutrino and gravitational wave connections, therefore, don't disprove the FRB mystery. They refine it, pointing us toward engines that are masters of efficiency, capable of focusing cosmic fury into a brilliant, fleeting, and surprisingly isolated radio whisper. Given the sheer number of galaxies in the observable universe, each potentially hosting the kind of cataclysmic events or volatile objects that create fast radio bursts, one might assume our skies would be absolutely ablaze with these signals. The math, when you first encounter it, is nothing short of staggering. Based on the current rate of detections and the fraction of the sky our telescopes monitor, astronomers estimate that a truly breathtaking number of these events occur across the entire cosmos every single day, somewhere in the neighborhood of several thousand. This calculation suggests that somewhere out there, a brilliant millisecond flash of radio energy is happening roughly every 20 seconds. This is not a rare or exotic phenomenon. It appears to be a fundamental and frequent feature of our universe's activity. And yet, this overwhelming estimated rate stands in stark contrast to the relative handful of events we've actually managed to catalogue. This glaring discrepancy forms a fascinating meta-mystery in itself. If FRBs are so common, why do we see so few of them? The answer to this rate mystery lies in a complex web of observational limitations, cosmic distances, and the very nature of the signals themselves. The primary and most immediate hurdle is the simple fact that our view of the radio sky is inherently limited. Even our most advanced radio telescopes, like the prolific CHIME array in Canada, cannot watch the entire celestial sphere at once. They are constrained by their field of view, a specific patch of sky they can effectively focus on at any given moment as the Earth rotates. It's like trying to observe a vast, dark field covered in randomly blinking fireflies while looking through a narrow cardboard tube. You might catch a few flashes in your immediate line of sight, but you are inevitably missing the vast majority of the show happening just outside your limited view. Furthermore, these telescopes aren't recording data continuously without interruption. They require maintenance, are subject to interference from terrestrial radio signals and Earth's own atmosphere, and often have their observational time divided among many different scientific projects competing for priority. All of these factors create significant dead time, periods when the instrument is not actively listening for these fleeting cosmic whispers, causing countless bursts to go completely undetected. Then there is the immense challenge of the signal's intensity and distance. Remember, the inverse square law is an unforgiving master of astronomy. A burst's brightness diminishes with the square of the distance it travels. So, an FRB that is utterly brilliant in its host galaxy, outshining everything around it, becomes an exquisitely faint whisper by the time it has crossed billions of light years to reach our antennas. Our telescopes are engineering marvels, but they still have a sensitivity threshold. We are only capable of detecting the very brightest, most energetic events from the most fortuitous distances. The thousands per day rate is an extrapolation based on these brightest events. For every one we see, there are undoubtedly hundreds or thousands of weaker, more distant bursts that simply fade into the universal background static before they can ever be registered by our equipment. Our current catalog is therefore heavily biased, representing only the most spectacular tip of a vast and mostly hidden cosmic iceberg. Another critical layer to this puzzle is the phenomenon of beaming. The radio emission from an FRB is not likely to be spreading out evenly in all directions like the light from a bare light bulb. Instead, it is almost certainly highly beamed, focused into a tight, narrow jet, much like the concentrated beam from a lighthouse or a laser pointer. This has profound implications for the observed rate. If the beam is very narrow, then it will only be visible from a very specific direction in space. The vast majority of these cosmic lighthouses will have their beams sweeping across the universe, but not pointed anywhere near Earth. We will only ever see the tiny fraction of bursts that happen to be aimed directly at us at the precise moment they go off. This dramatically reduces the number of detectable events and could easily explain why the actual observed rate is a small fraction of the estimated true rate. The universe could be teeming with these explosions, but we are blind to most of them simply because we're not in the right place to see the flash. This rate mystery is more than just an accounting problem. It forces us to consider the true prevalence and life cycle of the progenitor objects themselves. If the estimated rate of thousands per day is accurate, then the engine behind these bursts must be an incredibly common outcome of stellar evolution. It cannot be a rare, once-in-a-generation event in a galaxy. This statistical argument provides powerful, indirect support for the Magnetar model. Neutron stars, and by extension magnetars, are indeed common. There are likely hundreds of millions of them in our galaxy alone, and every galaxy will have its own population. A mechanism that allows each one to produce multiple bursts over its lifetime would easily satisfy the requirement for a high event rate across the cosmos. Every time we improve our telescope technology, widen our field of view, or increase our sensitivity, we pull back another layer of this veil, detecting more and fainter bursts that bring our observed count closer to that staggering theoretical number. Each new detection is not just another data point. It is a vote in a grand cosmic census, helping us to finally understand just how busy and violent our universe truly is when we have the right tools to listen. But perhaps the most profound question of all is not just where these bursts come from, but when. Each flash is a messenger from a specific moment in cosmic history, and by studying their populations, we can begin to ask, do the properties of fast radio bursts change over the billions of years of the universe's evolution? This inquiry into their age and life cycle opens up an entirely new dimension to the mystery, suggesting that the story of FRBs is not a static one, but a dynamic narrative that has been unfolding since the first stars were born. The clues to this evolutionary tale are written in their environments. As we've seen, many FRBs, particularly the prolific repeaters, show strong signs of being embedded in dense, turbulent nebulae, likely the supernova remnants from their own violent birth. This points toward a youthfulness, a phase of intense activity in the first few thousand years of a magnetar's life. In this stormy youth model, a newborn magnetar is like a cosmic toddler, prone to frequent and powerful tantrums as its crust adjusts to immense magnetic stresses and its environment is still chaotic with the debris of its formation. The bursts we see from these objects are brilliant, but they are also heavily scattered and distorted by the thick plasma cocoon they must punch through. Over hundreds of thousands of years, as the supernova remnant expands and dissipates into the interstellar medium, this local environment clears. The magnetar's outbursts might become less frequent, or perhaps cleaner and less scattered, as the signal has a clearer path to escape. Eventually, as the star's mighty magnetic field slowly decays over millions of years, the engine for these eruptions may sputter and die out entirely. This idea of an evolutionary sequence is incredibly compelling, but the data so far presents a messy and contradictory picture that refuses to conform to a neat timeline. We see some repeaters, like the original 1211-02, in a dwarf galaxy that is actively forming stars, a perfect setting for a young magnetar. Yet, we also have other repeating FRBs that have been localized to massive, settled spiral galaxies, where the dominant stellar population is older and quieter. These bursts appear to originate far from the busy star-forming arms, out in the galactic suburbs, suggesting their progenitors could be middle-aged objects that have long since drifted away from their birthing nebulae. How can a magnetar that is millions of years old still produce such violent outbursts? Does this imply that some engines can remain active for far longer than our models predict, or that there is a second, different mechanism at work for older systems? The search for answers extends beyond individual galaxies to the cosmos at large. Astronomers are now beginning to look for trends in the entire population of localized FRBs, asking if their properties correlate with the age of the universe itself. Do bursts from higher redshifts further back in time look different from those in the nearby modern universe? In the early cosmos, galaxies were smaller, mergers were more common, and stars were often born in frantic, intense starbursts. It's possible that the conditions were perfect for creating a larger population of highly magnetic neutron stars, or for triggering FRBs through more frequent stellar interactions. A burst from 10 billion years ago might be more energetic or more common than one from today. Conversely, if the mechanism requires specific metallicities or stellar types that evolved later, we might see FRBs become more frequent as the universe aged. Untangling this cosmic history is like trying to piece together the biography of an entire species from a handful of fossilized whispers, each one a fleeting glimpse into a different epoch. The frustrating and beautiful truth is that no clear timeline has emerged. The life cycle of an FRB progenitor remains one of the field's most open and engaging questions. Every new detection adds a new data point that can either fit a developing narrative or completely disrupt it. This isn't a failure of science, it's a sign of a rich and complex phenomenon. The diversity we see in host galaxies, burst morphologies, and repetition rates might all be reflections of where an object is in its life. A heavily scattered, highly active repeater could be a newborn. A clean, one-off burst with no repetition might be the final, fatal collapse of an ancient system, and a periodic repeater in an elliptical galaxy could be a rare, old magnetar in a binary system, being periodically rejuvenated by a companion star. The mystery of their age and evolution reminds us that the universe is not a static museum but a living, changing entity, and fast radio bursts are some of its most dynamic and unreliable narrators, each one telling a piece of a story we are only just beginning to understand. Imagine a perfectly clear lens made not of glass but of a shimmering, electrified fog, a dense cloud of charged particles drifting through space. Now picture a fast radio burst traveling through this ethereal lens. According to one of the most fascinating theories in modern astrophysics, this is not just a possibility. It could be the key to understanding some of the most bizarre signal morphologies we observe. This is the concept of plasma lensing, a natural cosmic amplifier that can twist, focus, and even split a radio signal in ways that defy simple explanation, creating effects so dramatic they could easily be mistaken for the source itself. The principle operates much like a mirage on a hot road. When light passes through layers of air of different temperatures and densities, its path bends, creating the illusion of water on the asphalt. In the case of plasma lensing, it's not heat but magnetized, ionized gas that does the bending. A dense, localized clump of plasma somewhere along the path between the FRB and Earth can act as a gravitational lens does for light, but with a crucial difference. Its effects are wildly dependent on the frequency of the radio waves. Lower frequencies are bent and delayed more strongly than higher ones. This frequency-dependent behavior can sculpt a simple burst into a complex, multi-peaked event. It could cause the same single burst to arrive at slightly different times, creating multiple images of the same flash, a phenomenon known as scintillation. It might also temporarily focus the radio waves, creating a brief but incredible amplification that makes a distant burst appear impossibly bright, as if the universe itself were turning up the volume knob for a split second. This theory elegantly explains some of the most puzzling FRB characteristics. That strange downward frequency drift seen in many repeating bursts where each sub-pulse plays a note lower than the last could be an illusion created by the lens. As the properties of the plasma cloud shift during the few milliseconds of the burst, perhaps agitated by the tremendous energy of the blast itself, it could progressively delay the lower frequencies more and more, creating the auditory effect of a cosmic slide whistle. The intense scattering that smears out some bursts into long tails could also be the result of the signal fighting its way through a turbulent plasma screen. Even the incredible brightness of some events might not be intrinsic to the source. They could be the lucky beneficiaries of perfect lensing alignment, their signals magnified by this natural interstellar telescope to appear far more powerful than they truly are. Yet, for all its explanatory power, the plasma lensing model demands conditions so precise they border on the miraculous. The required plasma clouds would need to be incredibly dense and compact, on scales similar to our solar system, yet able to maintain their structure against the dissipating forces of entropy and pressure. They would need to possess just the right gradient in density to focus the radio waves effectively without either absorbing them completely or being blown apart by the energy of the burst passing through. This degree of fine-tuning is itself a profound mystery. What natural phenomenon could create and sustain such perfect ephemeral lenses? The most likely candidate is the extreme environment immediately surrounding the FRB source itself, perhaps the glowing, energetic nebula powered by a young Magnetar spin, or the expanding shell of a recent supernova remnant. In this scenario, the lens is not a random interstellar cloud but a direct byproduct of the violent stellar physics that birthed the progenitor, a temporary structure in its dynamic and evolving cradle. The very existence of such lenses, if confirmed, would provide an unprecedented window into the micro-environments of these cosmic powerhouses, allowing us to probe their density, structure, and magnetic fields in exquisite detail. The lens is no longer just a distorting filter. It becomes a messenger carrying encoded information about the violent and beautiful neighborhood where these universe-spanning shouts are born. Yet, as if the frequency drift and scattering weren't clues enough, the very structure of a single burst can be a universe of complexity in itself. We arrive at a mystery that lives within the millisecond flash, the intricate internal architecture of an FRB. When we zoom in with the highest time resolution our telescopes can achieve, we discover that many of these events are not the simple, single spikes they initially appear to be. Instead, they unravel into intricate tapestries of multiple peaks, cascading subbursts, and fine-scale features that pulse and fade within the blink of an eye. This intrinsic variability is a direct window into the heart of the emission mechanism, a high-speed recording of the cosmic engine's most violent convulsions, and it challenges every simple model we have for how such coherent radiation is created. Consider the difference between the sound of a single firecracker popping and the rapid, sequential detonation of a string of fireworks. One is a simple impulse, the other is a complex performance with its own internal rhythm and structure. Many FRBs are the cosmic equivalent of that fireworks string. A burst might begin with a primary peak, followed by a series of secondary, smaller pulses that echo and ripple outward in time, each one a separate packet of energy released in a precise, though incredibly rapid, sequence. In some of the most spectacular examples, these subbursts can themselves be broken down into even finer microstructures, with variations occurring on timescales of microseconds, a millionth of a second. To put that in perspective, in the time it takes for a camera shutter to click, an FRB could perform an entire symphony of thousands of distinct micro-pulses. This isn't just a blast, it's a meticulously orchestrated, albeit ferociously fast, series of events. This level of intricate detail is a goldmine for astrophysicists because it rules out the simplest explosion-like models. A one-time cataclysm, like a singular neutron-star merger or a black hole evaporation event, would be expected to produce a much cleaner, single-peaked profile, a sudden rise and fall of energy. The complex, multi-peaked structure we observe points unequivocally toward a source that is dynamic and evolving during the few milliseconds of the burst itself. It suggests an engine that is undergoing multiple distinct episodes of energy release, or perhaps a single shockwave that is propagating through a structured medium, lighting up different regions in a rapid sequence. The leading theory once again points to the Magnetar and its tortured magnetic field. A starquake might not be a single, clean break. Instead, it could be a cascading failure where a fracture in the neutron star's crust triggers a chain reaction of ruptures along magnetic field lines. Each new fracture would release another bundle of energy, appearing to us as another sub-pulse within the main burst. Alternatively, the complex structure could be born from the way a plasma shockwave interacts with the dense, magnetized environment around the star, creating interference patterns and echoes that are then imprinted on the signal. The presence of this fine-scale variability also provides a powerful tool for diagnosing the environment right at the source. The shortest timescales we can measure, those microsecond variations place a strict upper limit on the size of the emission region. Because information cannot travel faster than the speed of light, a feature that changes in a microsecond must be generated in a region smaller than the distance light can travel in that time, a mere 300 meters. This is astonishingly compact. It means the incredibly complex dance of energy release powering an FRB is happening in a volume of space that could fit inside a small mountain, yet it's releasing more energy than our sun does in decades. This forces the emission process to be not just powerful, but also incredibly efficient and coherent, where particles act in unison like a laser to produce such bright radio waves from such a tiny source. Each complex burst, with its unique fingerprint of peaks and valleys, is therefore a detailed sonogram of the cosmic engine, allowing us to infer its size, its dynamics, and the storm of physics raging within it, all from a signal that has journeyed across billions of years to tell its fleeting, magnificent story. At the very core of every fast radio burst lies a property so strange it defies our everyday experience with light: coherence. This isn't just a bright flash, it's a laser-like shout, a blast of radio waves where countless trillions of photons march in perfect lockstep, their waves perfectly aligned and amplified. To appreciate why this is so baffling, consider the difference between an ordinary light bulb and a laser. A light bulb emits incoherent light photons of all different wavelengths and phases, spreading out in a disorganized jumble. A laser, by contrast, produces a tight, focused beam where every photon is identical and in sync, allowing it to travel vast distances without spreading out and fading. This coherence is what gives a laser pointer its ability to project a tiny, bright dot on a faraway wall. Now, imagine scaling that up to a cosmic level. An FRB is essentially a natural laser, or more accurately, a maser. It's microwave equivalent, but one operating on an almost unimaginable scale, generating a beam of coherent radio waves so powerful it can be detected across billions of light years. The central mystery is this: what natural process in the universe can possibly orchestrate such a collective, orderly dance of particles to produce this incredibly efficient and focused emission, and do it in a mere thousandth of a second? The sheer efficiency required is staggering. Coherent emission is the only way to explain how such a tremendous amount of energy is packed into such a narrow band of radio frequencies and beamed so effectively. Incoherent processes like the thermal radiation from a hot object simply cannot achieve this level of brightness. The energy would be spread out over too wide a range of frequencies and directions, rendering it far too faint to detect from another galaxy. To create coherent radiation, you need a way to make a vast number of electrons or other charged particles radiate in perfect unison, all oscillating together at the exact same frequency. In human-made lasers, this is achieved with precision mirrors and carefully prepared materials, forcing the photons into a synchronized state. In the chaotic, unpaved wilderness of deep space, achieving this same feat requires a natural engine of unbelievable precision and power. The particles need to be bunched together and then accelerated along a common path, much like a well-drilled army marching in step, so that their individual radio waves add together constructively, creating a single, amplified signal instead of a cacophony of random noise. Astrophysicists have proposed several compelling mechanisms to explain this, each pushing the boundaries of known physics. The leading candidate involves a phenomenon called stimulated emission, the very principle behind masers. In this model, the intense environment around a magnetar provides the perfect conditions for a natural maser. Imagine a cloud of excited particles within the neutron star's powerful magnetosphere. When a stray radio wave passes through this cloud, it can stimulate the excited particles to drop to a lower energy state, releasing a new photon that is an exact copy of the first one, same frequency, same phase, same direction. This triggers a chain reaction, an avalanche of identical photons, all reinforcing each other to create a colossal, coherent burst of radio waves. The magnetar's unimaginably strong magnetic field acts as the organizing force, channeling the particles and providing the energy pump to keep them excited, essentially turning a region of space the size of a city into a natural amplifier of cosmic proportions. Another fascinating idea involves the concept of bunching within a relativistic shock wave. Picture a cataclysmic event like a starquake on a magnetar's surface that launches a shell of material moving at nearly the speed of light. As this shell plows through the surrounding plasma, it creates a shock front, a cosmic sonic boom. Within this shock, electrons can be accelerated and forced to congregate into tight, discrete bunches. As these bunches of electrons move through the magnetic field, they are forced to wiggle, and because they are so close together, they radiate in sync, like a group of radio antennas all broadcasting the same signal simultaneously. This coordinated wiggling produces tremendously powerful, coherent radio emission. The timing and structure of the resulting burst would then be dictated by the dynamics of the shock wave and the spacing of these electron bunches, potentially explaining the complex, multi-peaked structure seen in so many FRBs. The challenge with all these models is that they require conditions so extreme they sit at the very edge of what we believe is physically possible. The magnetic fields must be strong enough to dominate the motion of every particle. The plasma must be dense enough to support the collective behavior, and the energy source must be potent enough to power the entire chain reaction almost instantly. This forces us to consider whether our current understanding of plasma physics and radiative processes is complete, or if FRBs are revealing glimpses of novel physics that only occur in the most violent crucibles of the universe. The coherent emission mechanism is not just a detail in the FRB story. It is the fundamental heart of the mystery, the precise reason these events are visible to us across such immense cosmic distances. Unlocking how nature builds its most powerful radio laser would not only solve the puzzle of fast radio bursts, but would also provide a new window into the most efficient energy transformation processes in the cosmos. If we could map the cosmos in its true form, we wouldn't see a collection of glittering islands separated by empty void. Instead, we would behold the cosmic web, a vast, intricate architecture of dark matter filaments, along which galaxies are strung like pearls on a necklace, and the spaces between them are filled with a diffuse, ionized gas known as the warm-hot intergalactic medium. This tenuous plasma is the universe's hidden skeleton, and for decades, astronomers have struggled to weigh it, map it, and confirm its very existence. Fast radio bursts, with their built-in cosmic odometers, the dispersion measure, were supposed to be the perfect tool to finally illuminate this shadowy realm. Yet, in a twist that has become wonderfully familiar, these brilliant flashes have revealed that our map of the cosmos is still missing fundamental landmarks, hinting at unknown structures and hidden components in the spaces we thought were merely empty. The principle is beautifully simple in theory. As an FRB's radio waves travel across billions of light years, they interact with every free electron along their path. The total number of these encounters causes the lower frequency waves to lag behind the higher ones, creating that dispersion delay. By measuring this delay, we get the dispersion measure, a direct count of the total number of electrons between us and the burst. Once we pinpoint an FRB's host galaxy and know its exact distance through other methods, we can calculate the expected number of electrons it should have encountered. This prediction is based on our best cosmological models, which describe an average, relatively smooth distribution of this intergalactic plasma. The expectation was that the observed and predicted values would match, finally allowing us to confirm the precise density and distribution of this elusive material, the so-called missing baryons that have confounded cosmologists. But the data has stubbornly refused to comply. Time and again, for a significant number of FRBs, the observed dispersion measure is noticeably higher than the predicted value for their distance. The radio waves seem to have traveled through more electrons than our maps of the cosmic web say should be there. This isn't a small accounting error. It's a consistent discrepancy that points to a universe that is far lumpier, far more structured, and filled with more material than our models have accounted for. The FRBs are acting as thousands of precision probes, sent on random journeys through the cosmos, and their collective report is telling us that the spaces between galaxies are not the near-perfect vacuum we imagined. Instead, they are dotted with previously invisible structures, dense clouds of warm gas, faint halos surrounding dark matter, or entire filaments of plasma that are too diffuse to emit light but are substantial enough to leave a fingerprint on a passing radio wave. This forces a dramatic rethinking of the large-scale structure of the universe. One compelling possibility is that we are detecting the vast gaseous halos that surround individual galaxies. Our previous observations might have severely underestimated the size and density of these coronas of hot gas. An FRB whose path skims the outer reaches of a galaxy, even one far from its visible disk, would travel through this extended material, picking up a significant extra dose of dispersion that our simpler models wouldn't have predicted. Another, even more profound idea is that we are finally tracing the true contours of the cosmic web itself. The standard cosmological model predicts that the majority of the universe's normal matter should be in this warm, hot intergalactic medium, distributed in a delicate foam of filaments and sheets. FRBs with anomalously high dispersion measures could be those whose paths have taken them directly through the dense knots at the intersections of these filaments, like a probe flying through the heart of a cosmic storm. The implications of this are staggering. Each well-localized FRB with a too high dispersion measure is not an anomaly. It is a single data point in a new kind of astronomy. By collecting hundreds and eventually thousands of these points, we can begin to do something previously impossible: create a three-dimensional mass map of the invisible universe. We can trace the outlines of the hidden gaseous filaments, weigh the dark halos of galaxies, and finally account for every last proton and electron that has been missing from our cosmic ledger. The dispersion measure Enigma, therefore, transforms from a frustrating puzzle into the most powerful tool in our arsenal. It reveals that FRBs are more than just mysterious explosions. They are the universe's own surveyors, casting brilliant flashes into the dark and returning with the first true charts of the cosmic deep, showing us that what we once called emptiness is in fact a teeming, structured, and magnificent hidden world. Yet for all their overwhelming power and brilliance, fast radio bursts are curiously solitary actors on the cosmic stage. We rarely see them sharing the spotlight with other spectacular transient events, which presents a fascinating puzzle all its own. If these bursts are born from the most violent processes in the universe, why don't they consistently arrive with an entourage? The search for these associations, for a supernova's lingering glow or a gamma ray burst's initial flash to coincide with an FRB, has been largely a story of absence, making the few potential links that have emerged all the more tantalizing and enigmatic. The expectation for a partnership seems logical. Many of the leading theories for FRB origins are intrinsically linked to cataclysmic, one-off events. If a burst is caused by the merger of two neutron stars, we would absolutely expect to detect the accompanying gravitational waves and a faint kilonova glow, just as we did with the landmark event GW 1908-17. If an FRB is the birth cry of a new magnetar emerging from the collapse of a massive star, it should be accompanied by the brilliant optical fireworks of a supernova, or at the very least, a long-duration gamma-ray burst. These are established cosmic partnerships. Extreme events tend to come in packages. The fact that FRBs overwhelmingly do not is a profound clue that their engine might be operating in a different way, or that we are missing a crucial piece of the timeline. This scarcity of associations forces a dramatic rethinking of the progenitor's nature. It suggests that the process creating the brilliant radio burst is either incredibly clean, channeling nearly all its energy into a very specific type of emission, or it is somehow disconnected from the main event. A supernova, for instance, releases the majority of its energy in neutrinos and visible light, with the radio emission from the expanding shockwave building up over weeks and months, not milliseconds. An FRB's radio flash is a tiny, incredibly intense spike happening on a completely different timescale. It could be that the FRB is not the supernova itself, but a secondary symptom, a magnetar having its first violent seizure within the first few hours of its life, buried deep within the expanding fireball of the explosion. By the time the supernova's light has brightened enough for our optical telescopes to see, days or weeks later, the brief radio flash would be long gone, leaving no obvious connection for astronomers to find. The rare instances where a potential association has been suggested are therefore scientific gold dust. One of the most compelling cases involved a relatively nearby repeating FRB that appeared to be located in a region of a galaxy that had hosted a supernova about a decade earlier. The timing was intriguing. Could the FRB be the recently born Magnetar now starting to act up? However, without a direct, simultaneous detection of the FRB and the supernova light, the connection remains speculative. It's a cosmic whodunit where the suspect was near the scene of the crime, but we can't prove they were there when it happened. Another tantalizing hint came from a study that found an excess of FRBs originating from the same general directions as known gamma-ray bursts, but again, without a precise, simultaneous detection. It's like hearing a shout and seeing a flash in the same city block. They might be connected, or they might be two separate incidents entirely. These elusive partnerships deepen the mystery significantly. They force us to ask, are we looking for the right companions? Perhaps FRBs are not paired with the loud, obvious transients we know, but with quieter, more subtle events we have yet to discover or classify. Or perhaps the association is not with the birth of an object, but with its death or a late-stage transformation we don't yet understand. The scarcity of clear associations doesn't isolate the FRB phenomenon. Instead, it weaves it into a more complex narrative, suggesting that these brilliant flashes might be the most visible part of a much deeper and darker cosmic process, one that prefers to hide its other movements in the silence between the bursts. And so we arrive at one of the most captivating and philosophically profound mysteries surrounding these cosmic enigmas, a question that taps directly into our deepest wonder about humanity's place in the universe. Could these unimaginably powerful, perfectly timed, and deeply structured signals be something other than natural? Is it possible that we are not just listening to the random eruptions of dead stars, but to something intentional? This is the technological versus natural origin debate, a line of inquiry that, while now largely set aside by mainstream science, forces us to confront the very limits of our understanding and the necessity of humility when facing the unknown. The idea first ignited imaginations not long after the initial FRB discoveries. Here was a signal that seemed almost engineered for detection across interstellar distances, incredibly bright to stand out against the background noise of the cosmos, astonishingly brief to be energy efficient, and located in a relatively quiet part of the radio spectrum. To some, these characteristics read less like a natural catastrophe and more like a beacon. The most famous and enduring hypothesis along these lines was proposed by astronomers at Harvard, who suggested that such powerful, focused bursts could potentially be evidence of alien technology, specifically giant light sails propelled across the galaxy by similarly colossal radio transmitters. In this vision, an advanced civilization might use a planetary-scale antenna to fire a concentrated beam of energy at a lightweight spacecraft, pushing it to a fraction of the speed of light. From our distant, fixed perspective, we wouldn't see the sail itself. We would only see the fleeting flash of the powerful beam as it swept across our line of sight, much like a distant lighthouse appears to blink for a sailor on the dark ocean. The repeating nature of some FRBs added more fuel to this speculative fire, as it hinted at a source that could be turned on and off, or perhaps was sweeping across our vantage point in a regular, predictable pattern. This line of thinking, while sensational, is not entirely without a scientific basis. It follows a principle known as the technosignature concept, the idea that we might one day detect evidence of intelligence not by picking up a deliberate message, but by accidentally observing the byproducts of immense engineering, much like an archaeologist might infer a lost civilization from the remnants of a road or an aqueduct rather than finding a written tablet. The sheer power required for an FRB certainly fits the bill for a project of Kardashev-type Roman II scale, a civilization capable of harnessing the entire energy output of its star. For a brief, thrilling moment, it seemed conceivable that we had stumbled upon the ultimate evidence that we are not alone. However, as the data poured in, the cold, hard light of evidence began to dim this exciting possibility. The final nail in the coffin for the artificial origin theory for most scientists was the discovery of an FRB within our own galaxy, emanating from a known magnetar. Here was definitive proof that at least one type of FRB, and by extension likely many others, had a clear, natural astrophysical origin. Furthermore, the incredible diversity of FRB properties became a problem for the technological hypothesis. Why would alien beams vary so wildly in their dispersion, scattering, bandwidth, and polarization? Why would some repeat with chaotic randomness, others with precise clocks, and most not at all? It seems an unlikely design for a coherent communication or propulsion system. The final argument is one of sheer statistics, with several thousand FRBs likely occurring across the observable universe every single day. Attributing them all to technology would imply a universe absolutely teeming with hyper-advanced civilizations all using the same, remarkably wasteful and seemingly pointless method of shouting into the void. And yet, to dismiss this idea entirely would be to miss its profound value. The technological origin debate serves a crucial purpose. It is a stress test for our own scientific biases and a reminder of the danger of premature closure. The history of astronomy is littered with examples of phenomena initially mistaken for artificial signals, from the pulsars dubbed LGM-1 for little green men upon their discovery, to the peculiar dimming of Tabby's star, which some thought might be caused by alien megastructures. In each case, the true natural explanation turned out to be far more strange and wonderful than anyone had imagined. The fact that FRBs so perfectly push our buttons, so closely mimicking what we might expect an alien signal to look like, is a testament to how little we truly understand about the extreme physics at work in our universe. It forces us to stay open, to not let our current models become dogmas. Perhaps there is a population of FRBs that still defy all natural explanation. Perhaps one day we will find a signal that is truly, undeniably artificial, buried within the cosmic static. Until then, the very act of considering the possibility, however remote, expands our imagination and ensures that our search for answers remains as wide and as curious as the cosmos itself. It is a debate that is less about little green men and more about the boundless potential for wonder in the human spirit. But with every new answer, the universe seems to pose a deeper, more complex question. We stand at a fascinating crossroads in our understanding, facing a paradox of progress that forms our final mystery, the future detectability puzzle. On one hand, we are in a golden age of discovery. Powerful new radio telescopes like CHIME in Canada and FAST in China are nothing short of revolutionary, acting as celestial fishing nets trawling the cosmic ocean and hauling in fast radio bursts by the hundreds. CHIME, with its massive, stationary array, constantly scans a huge swath of the northern sky, while FAST's immense 500-meter dish provides unparalleled sensitivity to fainter, more distant signals. These instruments have transformed FRBs from rare anomalies into a veritable population, allowing us to study their statistics, their distributions, and their bewildering diversity on an industrial scale. Yet, this flood of new data has not simply solved the mysteries, it has multiplied them. Each new detection adds another outlier, another exception to a rule we thought we were beginning to understand. The more bursts we find, the more we realize how much we underestimated the sheer creativity of the universe. We started with a simple question: what creates these bursts? Now we have a dozen more. Why do some repeat and others don't? Why do their rotation measures change so violently? Why do their structures vary from clean pulses to complex, multi-peaked cascades? The deeper we look, the more intricate the puzzle becomes, revealing layers of complexity we never anticipated. It's a classic case of the more you know, the more you realize you don't know. Our new telescopes aren't just providing answers, they are providing better, sharper questions. This leads us to an exhilarating and humbling prospect. as we build the next generation of instruments, even more sensitive arrays with wider fields of view and faster response times. What entirely new classes of FRBs might we uncover? Right now, our catalog is heavily biased toward the loudest, most obvious events. We are likely missing a whole menagerie of weaker, softer, or differently structured radio bursts that simply fade into the noise for our current technology. Future telescopes could reveal faint, repeating bursts from ancient, dying magnetars in elliptical galaxies, or ultra-high-energy, one-off blasts from the very edge of the observable universe, so distant their signals carry the imprint of the universe's earliest epochs. We might even discover bursts that exhibit properties we haven't even thought to look for yet, perhaps signals that are polarized in strange new ways, or that are linked to other cosmic messengers like neutrinos or gravitational waves in patterns we can't currently predict. The ultimate revelation might be that what we currently call a fast radio burst is just the most common, obvious type in a vast spectrum of radio transient phenomena. Just as the discovery of the first exoplanets shattered our simple model of solar systems and revealed an astounding diversity of worlds, the continued study of FRBs might force us to abandon the search for a single unifying theory altogether. Instead, we may find ourselves constructing a detailed taxonomy of radio bursts, each with its own distinct progenitor and mechanism, a family tree of cosmic explosions written in radio waves. The future of this field lies not in closing the book on these mysteries, but in eagerly turning the page to discover just how many more chapters the universe has left to write, each one promising to be stranger and more wonderful than the last. And so, after this incredible journey through 30 of the universe's most captivating secrets, what are we left with? We began with the fundamental origin problem, wrestling with the sheer violence needed to create such a flash, and we ended contemplating the very nature of reality, questioning if some bursts could even be echoes of cosmic strings or other physics beyond our current imagination. In between, we explored the stark divide between one-off bursts and repeaters, grappled with their prodigious energy output that defies belief, and followed the great debate that finally confirmed their extragalactic origins, only to be surprised by one in our own backyard. We saw how their dispersion measures reveal missing matter and their scattering tails whisper of turbulent stellar nurseries, while their missing counterparts and diverse host galaxies painted a picture of a phenomenon that can thrive anywhere. We dove into the curious case of the first repeater, 121102, with its persistent radio source, and then were baffled again by the precise clocks of periodic activity. We used their polarized light as a cosmic magnetic field probe and were perplexed by the bandwidth conundrum and the whimsical frequency drift that makes them sound like cosmic slide whistles. We witnessed the storm of hyperactivity from some repeaters and considered the compelling evidence for a bimodal distribution of two distinct populations. We puzzled over why they vanish at low frequencies and celebrated the galactic detection that gave us our first real answer, only to have it immediately raise new questions about energy. We inferred the extreme environments of their birth, used them as tools for cosmology to weigh the universe's missing matter, and decoded the magnetic pandemonium in their Faraday rotation. We listened for the deafening silence from neutrinos and gravitational waves and tried to reconcile their staggering estimated rate with the few we actually see. We explored the idea of their life cycle and evolution, considered how plasma lensing might be sculpting their signals, and marveled at the intricate internal architecture within a single millisecond flash. We confronted the heart of the mystery, their incredible coherent emission, and finally, we even dared to ask if they could be technological, a testament to the boundless human imagination that these signals inspire. What ties all 30 mysteries together is a single, beautiful truth. Fast radio bursts are not a puzzle to be solved, but a new language through which the universe is choosing to speak to us. Each detection, each new piece of data doesn't close a chapter, it opens a dozen new ones. They represent a living, breathing frontier in astrophysics, a field where every answer is merely a gateway to a deeper, more fascinating question. This is the very essence of scientific discovery, not a march toward a final destination, but an endless, wondrous exploration into the unknown. So stay curious. Follow the new discoveries as they happen, for they are happening right now, and share your thoughts. Which of these mysteries captures your imagination the most? Is it the possibility of alien technology or the terrifying power of a magnetar's starquake? The universe has given us 30 riddles written in radio waves. The greatest adventure lies in trying to read them together.